In this lesson, we are going to discuss bond polarity. Some bonds, some chemical bonds, are polarized. In other words, they have a positive end and a negative end associated with them. So, for example, you could have element A and element B that are bonded to each other, but the distribution of the electrons might not be equal to both A and B. So, in other words, let's say, for example, that B has a stronger attraction for electrons in the bond than does A. So if it has a stronger attraction for the electrons, then the shared electrons between them would be spending, so to speak, more time around B than they would around A. Consequently, if the electrons are kind of getting pulled towards B more so than A, then this side of the molecule would be negative and this side of the molecule would be positive. And that is what is referred to then a polar bond, positive pole and a negative pole. Now, how is that determined? So bond polarity can be determined first by understanding a concept called electronegativity. Electronegativity is an atom's attraction for electrons in a chemical bond. In other words, again, some elements have a stronger attraction for electrons than other elements. And that is given by an electronegativity chart that is on the periodic table, at least on the one that you will have for your quizzes and your tests. And the electronegativity, as it points out, as it shows in this example up at the top here for mercury, it's 1.9 for mercury. Now, the values of the electronegativity kind of trend from lower left to upper right on the periodic table. So the highest electronegativities will be in the upper right side, with the exception of the noble gases. Okay, so here we see fluorine has an electronegativity of 4, and that's because, and that will have the highest electronegativity. And these other ones, these are the noble gases. And the noble gases, since they don't have a real strong attraction for, or don't form chemical bonds very easily, at least the top 3 here, they don't have an electronegativity because they don't form a bond in the first place. But the rest of these do. But you can kind of see the trend here going from lower left to upper right is the electronegativity continues to increase here. Is from lower left to upper right, with the exception of the noble gases. So the noble gases, for the most part, we'll just assume them to be 0. And fluorine, which is in the upper right corner here, okay, so fluorine being in the upper right corner, will have an electronegativity of 4.0. Now, the electronegativity is on a unitless scale that just goes from 0 to 4. So the scale is simply from 0 to 4, and again, it's unitless. It's just been an arbitrary kind of scale. And when we then consider how atoms are bonded together, and we look at their electronegativity difference, we can determine then if a molecule is then going to be polar or nonpolar. So let's take, for example, nonpolar molecules. Now, nonpolar molecules would be molecules that then don't have polar bonds. So that means the electronegativities of the elements involved will be relatively close to each other. Let's take, for example, something like just oxygen, just O2. Now, if we look at the O2 molecule, then we'd have oxygen double bonded to itself. And the electronegativity of oxygen is 3.5. And of course, both oxygens will be 3.5. And when we're considering whether or not there is going to be a dipole in here, in other words, having 2 poles of a positive and negative, when we consider that, what we do is we look at the electronegativity difference. So we're going to look at the electronegativity difference here. And of course, if we take 3.5 and 3.5 and subtract the two, we're going to get obviously 0. Okay, so there is no electronegativity difference between those two oxygen atoms. So what that means is, if I have this oxygen atom, here's the nucleus of an oxygen atom, and here's the nucleus of another oxygen atom, and we look at the electron cloud that's then going to surround these two, all right, the electrons are going to be evenly dispersed between those two nuclei. So subsequently, there won't be a positive or a negative end to this molecule. If the electronegativity difference is less than 0.5, then the electrons are equally shared. And we say then that the molecule or the bond is non-polar. So there'll be an even distribution of the electrons in that kind of a molecule. So again, this is for we're talking about non-polar molecules here. Or excuse me, non-polar bonds. If, however, we have a molecule in which you have an uneven distribution of the electrons, it'll give rise to what is known as a polar bond. So if the electronegativity difference falls between 0.5 and 1.7, then the electrons are unequally shared, and we say then that the molecule or the bond is polarized or polar. So, for example, if we had a molecule, let's take something like fluorine and chlorine, if they were bonded together. Okay, if we had a molecule like this where we have fluorine and chlorine bonded together, and they'd form a nice little single bond here. Okay, if we looked at those, fluorine has an electronegativity of 4.0. Chlorine is 3.0. So if we look at the electronegativity difference for this bond right here, of course, it comes out to be 1.0. And this means that because 1.0 falls between 0.5 and 1.7, we would say that this bond is polar. So what that really means is the electrons will have a tendency to go towards the fluorine. Okay, so the electrons will have a tendency to be pulled towards the fluorine because the fluorine has a higher electronegativity. And again, the definition of electronegativity is an atom's attraction for electrons in a chemical bond. So fluorine's attraction for electrons in the bond would be greater than that of chlorine, and such that it'll actually pull the electrons towards it, not stripping the chlorine. They'll still be bonded, but then the chlorine will end up having a positive charge and the fluorine with a negative charge. And so we refer to this as a dipole, or two poles. So the molecule now might look something like this, where here you have chlorine and fluorine, okay, but the fluorine having a stronger attraction for the electrons will have perhaps a larger electron cloud around it, and as a consequence, it will be negatively charged and the chlorine positively charged. So we end up with an uneven distribution of these electrons in the molecule. But they're still bonded together. The fluorine and the chlorine are still bonded together here by a covalent bond. Now, what if it exceeds 1.7? So that brings us to the next part. So if it exceeds 1.7, then what's going to happen is the element that has the higher electronegativity will actually strip the electron from the other element, and you simply form two ions. So we form an ionic bond. So if the electronegativity difference is greater than 1.7, then it's an ion, then the electrons are transferred. Oops. To form ions. One of the simplest examples here might be something like sodium and chlorine. If we have sodium and chlorine bonded together, sodium has an electronegativity of 0.9, chlorine again is 3.0. So if we look at the electronegativity difference between these two, then we would get 2.1. And the 2.1 obviously exceeds the 1.7 here. So again, if it exceeds the 1.7, then what happens is the chlorine here, having the greater electronegativity, the greater attraction for the electrons, is going to pull that electron from the sodium. So we started off with the two being neutral, but then the sodium will give up its electron entirely to the chlorine. And what the result would be is a sodium ion and a chloride ion. Now that doesn't mean the two are not any longer bonded together. Now what you have is a positively charged particle and a negatively charged particle, and they're simply attracted to each other because they are oppositely charged particles. So to recap, what we have is we want to look at the electronegativity difference of the molecule, of the bonds, excuse me. So you want to look at the electronegativity difference that exists between the bonds. And if you have then electronegativity that falls between 0 and 0.5, okay, so if it falls between 0 and 0.5, what we're going to say is that this particular type of bond is going to be non-polar. If it exceeds 0.5 all the way to 1.7, then we say this is going to be a polar bond. So again, this is the electronegativity difference. Okay, so if electronegativity difference is between 0.5 and 1.7, we say it's polar. If it exceeds the 1.7, then it's going to be ionic. And both the nonpolar and the polar here are considered to be covalent. So again, the difference between a covalent bond and an ionic bond is in a covalent bond, electrons are shared. Here, electrons are transferred. Now the numbers again that I'm using, 0.5, is somewhat arbitrary. Again, depends on the textbook, but again, for this course, 0.5 is what we're going to use as the magical cutoff between polar and nonpolar. And then 1.7 is generally considered the cutoff between what's ionic and what is molecular or covalent. And that is bond polarity.